In this lesson we're going to look at the greenhouse gases and the greenhouse effect. And the first thing we need to sort of clarify here is that as far as AQA are concerned, there are three greenhouse gases. Okay, so we have carbon dioxide, methane and water vapor. Those are the three greenhouse gases. Okay, carbon dioxide, methane, water vapor. So we have our a graph here. This is quite a common graph, and it shows two different things. It's two different graphs rolled into one. On the x-axis, that is the same. We have time, okay? And on the y-axis here on the left, we have the temperature in degrees, the average global temperature. And when we mean average, we mean across the whole planet, across the whole year. Okay, so across all the seasons. So we're not talking about the temperature in one particular place on a particular part, on a particular day, like on a cold autumn morning. We're talking about the average global temperature for an entire year, and that is plotted here on the y-axis. And we also have the amount of carbon dioxide in the atmosphere. So we're essentially looking at two different graphs just overlaid onto each other. So we have the global temperature over time has increased. The general trend is an increase. The carbon dioxide levels over time has also increased. So whenever you're analysing a graph or describing the trend in a graph, the first thing you want to do is find the general trend. Okay, so in terms of the global temperature, it's all over the place. It's up and down, up and down, up and down. So to get the general trend, you look at the start point and you look at the end point. And you can see it has, over time, it has increased. So that is the first trend. For the carbon dioxide, it's a little bit simpler because it's not so erratic. You can see there's its start point and there's its end point, and over time it has also increased. So analyze the graph and write down any patterns you can identify and make at least one conclusion. So over time, both CO2 and average global temperature increase. Okay, so that is going to be the first thing we can take from that. And we can describe the amount it increased. So in terms of the carbon dioxide, this is not linear. Okay, it's an exponential increase. So we can talk about that. So the CO2 is increasing exponentially, which means that the rate at which it's increasing is going up. And again, we're looking at if we look at the gradient of the line, that gives us our rate, and the gradient is getting steeper, so the rate is increasing. So the rate at which the CO2 is increasing is getting greater and greater as time goes on. Now the average temperature is up and down, up and down, up and down. Okay, so the short term trend in average temperature is erratic. It's all over the place. If we were only looking at small sections, we probably wouldn't see much of a trend. It's only when you look at a large section of time that we can start to see that general trend, because it's all up and down, up and down. Okay, now you'll notice a little spike here for the CO2 and also a spike here in the global temperature, and history fans here will recognize that date. Okay, and this is all caused by World War II. But this isn't geography, so we're not hugely interested in that. We're more interested in the processes that are causing these changes. So over time, both the CO2 and the average global temperature have increased. The CO2 is increasing exponentially. The short-term trend in average temperature is erratic, we can see this spike here from World War II, but again, we can't actually infer that from the graph, from the data. We can tell it is using some outside knowledge that we have, but it's not directly something we can take from the graph. And the final thing we can say is, how do these two different trends relate to each other? Well, I would say that the carbon dioxide increasing correlates with the global temperature increasing. So they go in the same direction, so there is a positive correlation between CO2 and global temperature. So what is it called when two factors follow a similar pattern? Well, I've kind of given that away. It's a correlation. So the two sets of data correlate to each other. Now what I would say is, what we've got to be very careful of is correlation does not necessarily mean causation. Okay, so that graph is not saying, this is not irrefutable proof that increasing carbon dioxide causes increasing global temperature. It could be a complete coincidence. Okay, you could easily plot a graph of cases of sunburn over the year, and then plot a very similar graph saying number of ice creams sold over the year. And what you would find is a peak in sunburn in July and August, and probably a peak in ice cream sold in July and August. Does that mean that selling ice cream causes sunburn? No, of course not. They're just both things that occur in the summer months. So you've got to be careful not to jump to conclusions and jump to saying that, okay, because the data follows a certain pattern, this must be caused by that, when it's not necessarily the case. So yes, there is a correlation. Is there a causation? Not always. We have to look a little bit deeper to see if there is. So what we're going to be looking at is something called the greenhouse effect. And it's called the greenhouse effect because it's kind of a very similar process to how greenhouses work. So anybody who's been to a greenhouse, or has a greenhouse, or has grandparents that have a greenhouse, will probably be quite familiar with the fact that they're quite hot inside. Okay, they trap heat energy. And the way that they work is that the full electromagnetic spectrum of light from the sun can travel through the glass of the greenhouse. And it goes through the glass of the greenhouse, so all of that visible light goes through the glass of the greenhouse, and it's absorbed by the plants, by the ground inside the greenhouse. But it can't absorb all of that energy. Okay, so some of it is re-emitted, but once it's been absorbed and then re-emitted, it's lost energy. So it's now lower energy, and it's now not got enough energy in order to escape back through the glass. So we've got three different wavelengths of light that we're going to talk about. Okay, we have our short wavelength infrared light. This is high energy, and that's coming from the sun. And we also have the visible light, which is the rest of the visible spectrum. So the visible light and the high energy short wavelength, they can travel through the glass, not a problem. But the long wavelength infrared, now we should recognize infrared as being heat energy. Okay, so infrared light or infrared radiation is heat. So the long wavelength, low energy infrared cannot travel through the glass. Okay, but the short wavelength, the short wavelength light and the visible light can. The high energy light can travel through the glass. Okay, now some of that is immediately reflected and leaves, which is what you'd expect. Of course, the visible light can travel through the glass because you can see through it. You wouldn't be able to see through the glass if the visible light wasn't able to travel through it. So what happens is the high energy, the short wavelength light, is absorbed by the ground or by the plants and is re-emitted as long wavelength, low energy infrared radiation, which hasn't got enough energy to get back through the glass and is therefore trapped inside the greenhouse. And if that infrared energy or that infrared radiation is trapped inside the greenhouse, that means that the temperature inside the greenhouse increases. So looking at this diagram, what is the glass doing to each type of radiation? So the short wavelength light from the sun, okay, can travel through the glass. Not a problem. The long wavelength light reflected back from the Earth, so this long wavelength that has been re-emitted back from the Earth after it's been absorbed, cannot travel back through the glass. And is trapped inside the greenhouse. The visible light can travel through the glass. So all of this is a metaphor for how the Earth's atmosphere regulates heat. Now, the greenhouse effect is not a bad thing. We absolutely need the greenhouse effect. It keeps Earth at a habitable temperature. The problem is, as we are increasing that greenhouse effect, we are increasing the average global temperature, and that is having negative impacts. That is causing ice caps to melt and sea levels to rise and loss of habitats, stuff that we're going to talk about a little bit later on. So I don't want you to take away from this that the greenhouse effect is bad, because absolutely we need it. Without the greenhouse effect, we would not have habitable, wouldn't have a habitable planet, and we wouldn't have life on Earth. If you look at planets in our solar system, if you look at Mars compared to Venus, now Venus is closer to the Sun, so you would think it was hotter, but the average surface temperature of Mars is greater than Venus, even though Mars is further away from the Sun. And that is because Mars has a large amount of carbon dioxide in its atmosphere. Carbon dioxide is a greenhouse gas, which means that the atmosphere of Mars traps or absorbs a large amount of heat energy from the Sun, whereas Venus absorbs much, much less. So the greenhouse effect is happening with or without us. The problem is, if we increase the amount of CO2 in the atmosphere, or we increase the amount of methane in the atmosphere, two things that we are doing as a species, we're going to increase the greenhouse effect. We're going to cause it to absorb more heat energy. We're going to cause the global average temperatures to rise. So in this metaphor, the light is what it is. You have high energy, short wavelength light from the sun, okay? But the glass represents the greenhouse gases, okay? And remember, those greenhouse gases are carbon dioxide, methane, water vapor. So if we just replace that for a minute with a diagram. So if we have the Earth here, and we have the Sun over here, and then this can be the atmosphere. So the greenhouse effect essentially has four main parts. Number one, we have short wavelength, and we must talk about this in terms of wavelength, okay? So short wavelength, high energy radiation from the sun, okay, travels through space, through our atmosphere, and warms the Earth's surface. So it is absorbed by the Earth's surface. Okay, but only a very, very small fraction of it is actually absorbed, and the rest of it is re-emitted. Now, some of it is still quite high energy and is able to escape back to space. Okay, but some of it has lost energy. Okay, it's being re-emitted, but it has less energy now. So the third thing is long wavelength. Radiation is re-emitted. And what's important is that long wavelength radiation, that low energy, long wavelength radiation, is not able to escape our atmosphere. Now, the way this is different to the metaphor of the greenhouse is it's not trapped by glass or anything like that. It's absorbed, and it's absorbed by the greenhouse gases. Okay, so this long wavelength radiation is absorbed by greenhouse gases. So those are our four main steps. So short wavelength, high energy, radiation from the sun travels through space, through the atmosphere, hits the Earth's surface, it's absorbed by the Earth's surface, which warms it up, and it is re-emitted back to space as long wavelength radiation, and that long wavelength radiation is absorbed by greenhouse gases, and those greenhouse gases are carbon dioxide, methane, and water vapor. Okay, and the more carbon dioxide, methane, and water vapor we have in the atmosphere, the more of this infrared radiation they're going to absorb, and the higher the average global temperature. So let's turn this into a flow map then. So the first step is short wavelength, high energy, radiation from the sun, hits the Earth's surface, and is absorbed, and that warms the Earth's surface. It is re-emitted as long wavelength, low energy, infrared radiation. This is absorbed by greenhouse gases. Carbon dioxide, methane, and water vapor. So 1, 2, 3, 4 steps, and it is really, really important that we are using the key terminology here, that we are talking about short wavelength radiation from the sun. It hits the Earth's surface and is absorbed. It is re-emitted as long wavelength infrared radiation, and this is absorbed by the greenhouse gases. It is not trapped and it is not reflected by the greenhouse gases. So 4 steps to the greenhouse effect you need to make sure that you know and that you are familiar with. And let's just make sure we use all our key words. Did we mention infrared? Yes, we did. We mentioned absorbed. Yes, we mentioned carbon dioxide, greenhouse gases, short wavelength, long wavelength. This is key terminology that you must be using in your answers.